Okay, I think we are live now. Stream manager. Yeah, I'm still learning how to stream on Twitch. I see on my iPad there is some stream manager which show me activity feed, chat. I think we are fine with it, but maybe just maybe I would like to check the sound so I can go to my own stream. Okay, I think I can hear myself, so we are fine. I will back to the stream manager and let's back to our Rust learning. So today I would like to cover data types, at least maybe functions as well. So this is 3.2, 3.3. This is my plan. It's like for my second stream. So let's start. So data types. Every value in the Rust of a certain data type, which tells Rust what kind of data is being specified, so it knows how to work with the data. We'll look at two data type subsets, scalar and compound. So yeah, basically type languages is great. Like I start my career with Objective-C, and yeah, I do some mobile development, macOS development, etc. Then I had experience with PHP, JavaScript, and I feel it kind of fine to have like dynamically typed languages and things like this, but once I switch from JavaScript to TypeScript, I don't see the way I can back to JavaScript again, because types give you so much power, like so much stability, like it's cover so many problems. It's like in the long term, if you just trying to do things like quickly, maybe do some one-day demo, yeah, maybe you don't need types. But once you back to your code since a while, 1 month, 2 months, maybe a year, and then you need to change the logic, and you don't know what fields you're missing, where this typo and things like this. And this is where strengths of types, many other places can help you. So types are great. Let's learn the Rust types. So keep in mind that Rust is statically typed language, which means that it must know the types of all variables at compile time. The compiler can usually infer what type we want to use based on the value and how we want to use it. In cases when many types are possible, such as when we converted a string to a numeric type using parse, we saw it in the second chapter, programming and guessing name. We must add a type annotation like this. So the variable u32 and parse and error handler. Okay. If we don't add u32 type annotation shown in the preceding code, Rust will display the following error, which means the compiler needs more information from us to know which type we want to use. So yeah, I think it's a good thing to try everything, and let's actually try it. So let guess and just try to run it. Could not compile variables due to previous error. Type annotation needed. Okay. Consider giving guess an explicit type. Okay. And as usually, we try suggested features so we can be more familiar. Oh, actually, it's a lot of text here. The compiler could not infer a type and ask for a type annotation. Error code example. This error indicated that type inference did not result in one unique possible type and extra information is required. In most cases, this can be provided by adding a type annotation. Sometimes you need to specify a generic type parameter manually. A common example is the collect method on iterator, etc. So yeah, basically I'm not gonna read everything, but just okay, there's some error. I see, maybe I need just restart Vim. I changed my key binding, so now yeah, sorry, let me test. Yeah, everything is working. So yeah, let's try the fix there. By the way, Rust Analyzer didn't prompt us this error, but we see it compile time. So cargo run. Yeah, we are good. You'll see different type annotation for other data types. So scalar types. A scalar type represents single value. Rust has 4 primary scalar types: integers, floating point numbers, booleans, and characters. You may recognize this from other programming languages. Let's jump into how they work in Rust. Okay. Integer types. An integer is a number without a fractional component. We used one integer type in chapter 2, the U32 type. This type declaration indicates that the value it's associated with should be an unsigned integer. Signed integer types start with I instead of U. That takes up 32 bits of space. Table 3.1 show the built-in integer types in Rust. We can use any of those variations to declare the type of an integer value. Let's see what we have here. The signed, unsigned, 8, 16, 32, 64, 128. What is arc? I don't really know. It might be something depends on implementation of the system or something like this. I don't know. Maybe we will find out later. But let's try something. Can we just... yeah, let's just... hide all of this. And play a bit with our variable. Not used. That code. Yeah, everything works. And what the smallest one? Maybe something like this. Okay, and what happened if we have bigger number than 8 bits? What is the biggest number of in Rust? Yeah, 255. So let's try 156 and see what happened. The thread main panicked at not a number, so if the number is bigger than our type, it will error. Okay, and yeah, with sign it it's kind of half, but for unsign it works. Okay. So for sign it will be something like, how about this? And $128 will fail. Yeah, basically got it. We are fine. So each variant can be either signed or unsigned and has an explicit sign. Signed and unsigned refers to whether it's possible for the number to be negative. In other words, whether the number needs to have a sign with it, signed, or whether it will only ever be positive, and can therefore to be represented without a sign, unsigned. Yeah, we kind of discussed it. It's like writing number on paper. When the sign matter, a number is shown with a plus sign or minus sign. However, when it's safe to assume the number is positive, it's shown with no sign. Signed numbers are stored with two component representation. And here is the link. What is the link to complement? Is So yeah, this is, if you would like to know more about how it's implemented in mathematics. I actually already don't remember. I did it in the university, but not use it for a while. Basically, what happened, we have like 8-bit, and with unsigned it used representation. All 8 bits used for representation of a number. So the max number of unsigned 8 is 255. It's like 2 power 8. So it's like 256 and minus 1 because we also have a 0. We start from 0. And for the signed I8, we use 1 bit we use for store is it positive or negative. So the max will be 2 power 7. So as we tried here, it's 128. So basically it's from minus 127 to 0 and to something like this. So possible might be something like this. I'm not sure. Let's actually try it. So if we have I8, can we have minus yeah, we can have, so it actually will be from minus 128 to positive 127. So which is, yeah, thanks Copilot, it's 256 in total, which is actually our bits to power 8, our 8 bits. Cool. Okay, it's actually explained here. I wasn't neat. Yeah, but this is nice way, I think, like you try to think about the information you get, you try and explain it yourself first, it makes you understand what you read better. So yeah, so we can read it now in the book. Each signed variant can store numbers from blah blah blah, inclusive, where n is the number of the bits that variant uses. So an i8 can store number from, yeah, this is exactly what we had. Look, this is minus 2 power 7 and 127, 2 power 7 minus 1. Exactly. Unsigned variants can store numbers from 0 to power n minus 1, so U8 can store numbers from 0 to 255. Additionally, I size and U size types depend on architecture of the computer your program is running on. So let's back. Okay, yeah, this is what I thought. The arc means architecture, so based where it will be run, maybe some embedded devices or whatever it is, you don't know, so it will be picked up maybe at compilation time. But yeah, at compilation time you already know what architecture it will be. So this is it. Depends on the architecture of the computer your program is running on, which is denoted in the table as arc. 64 bits if you're on the 64-bit architecture, and 32 bits if you're on the 32 bits architecture. You can write integer literals in any of the forms shown in table 3.2. It's our table 3.2. Integer literals, decimal. Yeah, sorry, I don't really get what I read just now. You can write integer literals in any of the forms shown in table. Note that number literal that can be multiple numeric types allow a type suffix such as 7 to designate the type. Number literal can also use as a visual separator, underscore as a visual separator to make the number easier to read, such as 1_000, which will have the same value as you had specified. Okay, so with underscore we can separate like thousands from the number under thousands. So basically formatted, and we can write which will be basically 1000 or yeah, this one will be just 98,222. Let's confirm it on practice. So cargo run, and you see formatted is 1000 and 98,222. Okay, now hex. Let's try hex. And you see it's basically f is 16 power 1 plus 16 power 0. Or not. Okay, maybe I need to recheck how the different digit systems works, but basically yeah, let's confirm the number. We have the error. Okay, yeah. And yeah, this is actually max number of 2 hex FF. Okay. But anyway, basically we can write number and hex representation. It can be marked as U8 yeah, and it should give us an error. Yeah, it immediately says it's does not fit I8. Okay, this is cool. So octal, binary, and the byte. Actually never use something like byte. Not sure how it works. B and A in quotes. Let's try this one. Okay, it's 65. Is 65 is representation of A in, okay, yeah, Copilot knew it. It's 65 is the code of A, upper letter A. Let's try with lowercase. I think it should be different code. Okay, and you see now it's 97. Yeah, it's just a representation of character in ASCII character system, encoding system. Yeah, this is what it is. Yeah, I haven't learned in that deep any data types for a long time. I think it's something like similar to university times when I learned C++ or something, which I completely don't remember now, but it's quite interesting. It's like latest years, recent years, I just watched some tutorials, crash course of Rust or anything, just to try quickly start writing some code. But it's so much fun to learn the basics in depth, just reading the book. This is interesting experience. So how do you know which type of integer to use? If you are unsure, Rust defaults are generally a good place to start. Integer type default to i32. The primary situation in which you use isize or usize is when indexing some sort of collection. Okay. Integer overflow. This is something we already tried. 256 overflow U8. So let's read what this says here. Let's say you have a variable of type U8 that can hold values between 0 and 255. If you try to change the variable to a value outside the range, such as, yeah, exactly what we did, 256, integer overflow will occur, which can result in one of two behaviors. When you are compiling in debug mode, Rust includes checks for integer overflow that cause your program to panic at runtime if this behavior occurs. Rust uses the term panicking when a program exists with an error. We'll discuss panic in more depth in the unrecoverable errors with panic section in chapter 9. Okay, I think we will be there at some point, but we just at chapter 3, so let's don't think about too deep. When you are compiling in release mode with the release flag, Rust does not include checks for integer overflow that cause panics. Instead, if overflow occurs, Rust performs two's complement wrapping. This is the Wikipedia link on this term. In short, value greater than a maximum value that type can hold wrap around to the minimum of the value that can hold. In the case of in case of U8, the value 256 becomes 0. The value it's like becomes 1. It's interesting, and so on. Okay, I think I get it. So in binary representation, so binary max you see it will be like this, and binary overflow it will be like this. Okay, actually I already like this underscore feature. It's so much sound vocal, I would say. Yeah. So and now we have this, and in case of release mode we will just drop everything the bigger our 8 bits, and it just will be 0, so it will be like this. And for number 257 we drop it and it will be just 1, exactly what we just read. Okay, I got it. The program won't panic, but the variable will have a value that probably isn't what you were expecting it to have. Relying on integer overflow wrapping behavior is considered an error. To explicitly handle the possibility of overflow, you can use this families of method provided by the standard library for primitive numeric types. Wrap in all modes with wrapping method, such as wrapping add. Return the none value if is overflow with checked method. How I actually can wrap in add? So let's try wrapping try. So this is basically function wrapping add binary max binary overflow, which right now is just one, but it's good enough. So let's print the result. There's some error I don't really understand at this point. So wrapping add is unstable library feature, so it's not recommended to use. Okay, automatically import it from the intrinsics, which is unstable. Maybe yeah, code action don't provide us different import, so I guess it is what it is. Okay, maybe we will let back to this later. Because yeah, it's not really clear how I can use it. Generally, what it says, if you want to avoid overflow, you should use some special functionality. So maybe we will try to find out about it deeper when we need it. Let's go to the floating point types. So Rust also has two primitive types for floating point numbers, which are numbers with decimal points. Rust floating point types are F32 and F64, which are 32 and 64 bits in size respectively. The default type is F64 because on modern CPUs it's roughly the same speed as 32, but is capable of more precision. All floating point types are signed. Here is an example that shows floating point number in action. So by default it's float 64, and if you want to explicitly use 32 bits, then we have to directly specify it. Okay. If you want to know more about how this 32 or 64 bits stored in the memory, you can learn this standard. We don't want to do this right now. I think we just can try to type it, and that's it. Let float number. Okay, we're already using camel case, so let's have float number. Let's print it with our macro cargo run. Okay. Remove this part which is provide us error. Float number is 2. Maybe it's actually recommended to use snack name. So I like this way when inbuilt standards of naming things, so it will be more consistent in the long term. Okay, didn't save it. Okay, now we see it's actually float. And now numeric operations. Rust support the basic mathematical operations you expect for all number types: addition, subtraction, multiplication, division, and remainder. I actually didn't know how it called in English. I guess this is remainder. Oh, it's remainder. Sorry, guys. Okay. Yeah, reading books helps you to learn new words. So integer division truncates 0 to the nearest integer. So Let's try. Yeah, just comment everything we don't need at the moment. So what we wanna try? Division. And we should have one. Let's find out. Yeah. Let's read the rule again. Division truncates toward 0 to the nearest integer. So it don't care, just if we change it from like this, yeah, it's still 1, so it just drops, even if it will be like something. Okay. The following code show you how you use each numeric operation in let statement. Okay, here is example how it's truncated. Maybe let's try remainder. So the result is 3, I guess. And yeah, it is, as you can see, it is 3. Each expression in the statement uses a mathematical operator and evaluates to a single value, which is the bound to a variable. Appendix B contains a list of all operators that Rust provides. Let's have a look. So the plus, multiplication, division, maybe let's try this one. So we need to make our variable mutable, so mut then division. Yeah, Copilot already knew what I wanted. So result 6 exactly. Division is 6. Okay, what else we have in appendix? Just to the future reference, if we need something we can quickly review it. Okay, non-operator symbols. Okay, now the Boolean type. As in most other programming languages, a Boolean type in Rust has two possible values, true and false. Booleans are 1 byte in size. The Boolean type in Rust is specific using bool, for example. Yeah, pretty straightforward. Yeah, it's not like if we have false here, it's not require, but just for example. So LSP can say it's bool, and if we change it to false, it still can say it's Boolean, and we can directly specify it's Boolean. So and what it complain about, unused. Okay. We can remove the warning with underscore. It says if this intentional, prefix it with underscore. Okay. Maybe we will need it at some point. Yeah, Boolean is quite simple, so I don't think we need to dive deeper. The main way to use Boolean value is through conditional, such as if expression. Will cover how if expression work in Rust in the control flow section. Okay, it's this chapter, control flow. We will be there soon. The character type. So Rust's char type is the language most primitive alphabetic type. Here is some examples of the declaring char values. Okay. Char A. What if we have AA? It's one character long. Okay. Here we are. An emoji, one character as well. Okay. Note that we specify char literals with single quotes as opposed to string literals, sorry, which use double quotes. Rust. Okay, if we want to string. We will do double quotes. And this one is fine. And what is the type here is reference str. Okay. So Rust chart type is 4 bytes in size and represent a Unicode scalar value, which means it can represent a lot more than just ask how it's actually pronounced. Let's try. Okay, can't hear sound here. Play with it later, maybe. Accented letters, Chinese, Japanese, Korean characters, emoji, and zero with spaces are all valid char values in Rust. So basically we can put some Japanese char. So what we can do here, we can select Japanese and copy this one. And we can print it without any problem. Yep. This is how it looks. Unicode scalar values range from So can we just use something like this, put it in the while, yeah, it asks next case. No, it's not something stupid I did, so maybe it somehow can be converted, I don't know. However, a character isn't really a concept in Unicode, so your human intuition for what a character is may not match up with what a char is in Rust. We'll discuss this topic in detail, storing UTF-8 encoded text with string in chapter 8. Okay. We can postpone it until the time comes. compound types. Compound types can group multiple values into one type. Rust has two primitive compound types, tuples and arrays. The tuple is general way of grouping together a number of values with a variety of types into one compound type. Tuples have a fixed length. Once declared, they cannot grow or shrink in size. Okay. So basically I using tuples in TypeScript in React. If I open, I don't know, some components, maybe yeah, you see it's tuple because React it kind of force you to use it with default hooks, but I never really learned what it is, so maybe Rust will help us in this question. We create a tuple by writing a comma-separated list of values inside parentheses. Like this. Each position in the tuple has a type, and the type of the different values in the tuple don't have to be the same. We've added optional type annotation in this example. So basically we don't need annotation, just for the visibility. Tuples, tuple. How would correctly name tuple? Tuple check. Okay. LSP, aka language processor server, can say us it's i32, f64, i32. But we can explicitly say it's i32, f32, i32. Okay. The variable tup binds to the entire tuple because a tuple is considered a single compound element. To get the individual values out of tuple, we can use pattern matching to destructure a tuple value like this. Yeah, this is what we should practice. Tuple destructuring x, y, z. And of course, println. we don't want print everything, maybe skip y and yep. And what suggested here? Okay, if we're not really going using y, we can use prefix underscore here. Yeah, it brings some visibility, so when you read the code you can, okay, I need it here to correctly destructure this type, but I don't really worried about it anymore because it's used with underscore. What if I use it here? No, it's not actually works as I thought. Just hide there. It doesn't mean we're not going to use it, but what if we will do it like this? Can we do it like this as well? So yeah, just mark it as it is. Okay. And what if I do so the x is a tuple now. It's interesting. Okay, we can reach it by index. This program first creates a tuple, binds it to variable tup. It then uses pattern with let to take tup and turn into 3 separate variables. This is called destruction because it breaks the single tuple into 3 parts. Finally, the program print value of y. We can also add such tuple element directly by using period. Yeah, we already learned it. Actually. We are good. We're discovering things ourselves. This program creates tuple x and then access each value of tuple using their respective indices. It is most programming language. The first index in a tuple is 0. The tuple without any values has a special name unit. This value and its corresponding type are both written parentheses and represent an empty value or an empty return type. Expressions explicitly return the unit value if they don't return any other value. So this is the unit, and for example our function calculates some tuple value, and in case it's not possible but we still want return tuple, just return empty parent house, which is unit, I guess. Okay. The array type. Let me drink some water. What the stream manager says. Okay, it's already over 1 hour online. So yeah, sorry, let's back to our array type. Another way to handle a collection of multiple values is with an array. Unlike a tuple, every element of an array must have the same type. Unlike arrays in some other language, arrays in Rust have a fixed length. Okay. We write the values in an array as a comma-separated list inside square brackets. So yeah, pretty common look. Let array with some random numbers and let's check the type. Type look like this. I32 semicolon 5 is the length. So if we want I64 5, no, no, it's not like this. Let's read a bit more about it. Oh, I see down here it's semicolon. So we can do it like this, and if we change the length we will get an error. So which can be useful because like for example for Copilot, like we have random array with 8 elements and Copilot just do it for us. Or we went 20, sorry, and Copilot do it for us. yeah, I think it's handy. I like it. Arrays are useful when you want your data allocated on the stack rather than the heap. We'll discuss the stack and heap more in chapter 4. Yeah, stack and heap, it's quite interesting. It's something that discover how actually our software works under the hood. So yeah, I'm excited about it actually. Because as I said earlier, I didn't really dive in these topics since like university, like 13, 14 years ago. Like, don't really need it, for example, in TypeScript now, so that's why we're here. We're learning Rust to dive deeper. Or when you want to ensure you always have a fixed number of elements. An array isn't as flexible as vector type. So, vector is similar collection type provided by the standard library that is allowed to grow or shrink in size. Sorry, I didn't mean to click it. Maybe let's open in the new link. Yeah, so if you need dynamic size, you just use the vector type, which is part of standard library. This is sound okay. As usually, wait to chapter 8 to dive into it deeper. However, arrays are more useful when you know the number of elements will not need to change. For example, if you were using the names of the months in program, you would probably use an array rather than a vector because you know it will always contain 12 elements. Write an array type using square brackets with the type of each element, a semicolon, and then the number of elements and the array like so. We already tried this one. Here is I32 is the type of each element. After the semicolon, the number 5 indicates an array contained 5 elements. You can also initialize an array to contain the same value for each element by specifying the initial value followed by a semicolon, and then the length of the array is square brackets as shown here. The array named A will contain 5 elements that will all be set to the value 3 initially. This is the same as writing let A, but in more concise way. So the value and the length. Let's try this. Let's have 10 here. 5 here, and of course we will check. No, we cannot print. Pretty print. Okay, something Yeah, it's like 10 elements, all is 5. Okay, so we can access elements. An array is a single chunk of memory of known fixed size that can be allocated on the stack. You can access elements of an array using indexing like this. Basically, let's print false elements. So yeah, you can see it here. Okay. In this example, the variable name first to get the 1, and this will be 2. Okay. Invalid array element access. So let's see what happens if you try to access an element of array that is past the end of the array. Say you run this code similar to the guessing a number to get an array index from the user. So we have an array, we have some input index. I want to try this. Let's okay, let's import IO dependency and let's run. Please enter index array 10. Index autobound. This code compiles successful. If you run this code using cargo run, the program will print all the corresponding value of the index and array. If you instead enter a number past the end of the array, such as 10, you'll see output like this. Run resulted in runtime error at the point of using the invalid value in the indexing operator. The program exited with an error message and didn't execute the final println statement. When you attempt to access an element using indexing, Rust will check that the index you specified is less than array length. If the index is greater than or equal to the length, Rust will panic. And panic we will learn later, somewhere. Some chapter, I think. This check has to happen at runtime, especially in this case, because the compiler can't possibly know what value a user will enter when they run the code later. This is an example of Rust's memory safety principles in action. In many low-level languages, this kind of check is not done. And when you provide an incorrect index, invalid memory can be assessed. Rust protects you against this kind of error by immediately exiting instead of allowing the memory access and continue. Chapter 9 discusses more Rust error handling and how you can write readable, safe code that neither panic nor allow invalid memory access. Yeah, this is maybe the biggest problem of the C++. Maybe not biggest problem. I'm not like C++ developer, but not for time ago I just like watch some tutorials about C++ types, and you can try to print like what we can do. We can do something like integer value, don't initialize it, like, okay, and then you can just print it and it will just take random value from the memory. This is super weird. Like, if it like in hello world program, it's not a problem. You see something wrong, you can just okay, oh, I forget it might be this variable not initialized. But when it's super complex application and this application start behave super weird, it just instead of expected value it gives some random value and you don't understand what's going on. So this is really bad, I think. Okay, this was our data types chapter. Next we will go to the function, but yeah, I think it will be on the next stream. Not sure when I have time yet, but yeah, we will try to have some consistency on the streaming, learning Rust. Thank you for watching. See you next time.